A vision transformer never sees an image as one pixel grid. Timm turns patches into tokens, and PyTorch attention combines them into a class prediction. You'll see how to connect the pieces into a workflow that turns image patches into embeddings and explains the chosen label. I'm Professor Pi, teaching AI foundations with simple Python. Vision transformers answer a straightforward gap in image classification. Convolutions scan local neighborhoods. VIT chops the image into fixed tiles and treats each tile like a word. Attention then lets every tile talk to every other tile, giving the model global context. People reach for this when they need flexible long-range reasoning, or when they plan to scale up with lots of data and transfer learning. The timm library fits perfectly here because it gives ready-made VIT variants and exposes internals we can poke at without rebuilding everything. Picture patching as cutting a photo into square postcards. Each postcard becomes a vector. One postcard, the class token, acts like a shared mailbox where the model collects global evidence. Attention decides which postcards matter for the final label. The upside is clear global reasoning and modularity. The downside is data hunger and sensitivity to patch size. For small experiments, the practical move is to freeze most of the backbone and only train a classifier head. We'll build a compact, inspectable pipeline. First, convert a toy image into patch tokens so you can see the token shapes. Then, prepend the class token and watch how it mixes with patches. Next, capture a raw attention snapshot from the first transformer block. After that, fine-tune only the head on two tiny images. Finally, run a minimal training loop and show predictions. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. To start, we need to see how timm turns an image into patch embeddings. So the first snippet isolates patch embed and prints shapes. This snippet uses timm to convert one simple image into patch tokens. The VIT doesn't begin with a class label. It first chops the image into fixed-size patches and projects each patch into an embedding. The call to timm.createModel gives us a small vision transformer, and model patch embed exposes that projection step directly. The red square in IMG is deliberately visible in the tensor slice, so you can confirm the input isn't random. The printed output shape tells you how many patch tokens you have and how wide each token embedding is. The model now needs a place to collect image-level evidence. So next we will add the learned class token ahead of the patch tokens. This example shows how to prepend the class token to the patch sequence and why that matters. Patch tokens carry local content, but a classifier wants a single vector that summarizes the whole image. In timm, model.cls token is learned by the VIT, and torch.cat places it in front of the patch tokens exactly the way the model does internally. Token count becomes one larger than the patch count because the class token joins the sequence. And printing class norm gives a quick sanity check that the special token is a genuine learned vector, not an empty marker. That norm reassures you the token will meaningfully participate in attention updates. We can inspect attention to see which patch the class token looks at first, so the next snippet captures a head-level attention snapshots from the first block. This code captures where the class token looks inside the first timm transformer block. The model's forward normally returns logits, not intermediate attention, so a PyTorch forward hook on model.blocks.0.atten.atten_drop records the attention tensor during model image. Then, CLS to patch reads the class token row and averages across heads to give a simple view of which patch the class token attends to first. It's a lightweight diagnostic, not a full explanation method, but the output names the patch with highest captured attention and the score behind that choice. Inspecting attention shows which regions matter, but we still need a trainable head to map tokens to labels. And training the whole backbone is expensive on tiny data. So next we will freeze the backbone and train only the head with a tiny batch. This snippet fine-tunes the classifier head while leaving the token-making backbone frozen. Updating the entire VIT can be costly and unstable on very small data. So the code first disables gradients for every parameter and then re-enables only model head. The batch here contains 2 simple images and labels, enough to show supervised classification mechanics without pulling in data loading boilerplate. Torch optim atom W updates only the head parameters after cross-entropy compares logits to labels. The printed head loss confirms the model produced a trainable classification error. Finally, we will stitch the pieces into a minimal training and prediction loop so you can see the end-to-end behavior in one flow. This code turns the pieces into a tiny end-to-end VIT classifier baseline. The same timm model now repeats the basic training loop. Clear gradients, run tokens through the transformer and head, compute cross-entropy, backpropagate, and step opt. After training, model.eval and torch.nograd switch into prediction mode, so printed results aren't affected by gradient tracking. Softmax converts logits into class probabilities, while pred shows the chosen class for each toy image. The output demonstrates that token embeddings, the class token, and the fine-tuned head together produce visible class predictions. In a practical project, you'd swap the toy images for labeled samples, use a proper data loader, and expand the training epochs. The same inspection steps scale up. Those hooks and prints work on larger batches and help you visualize attention across real images. Summing up, a vision transformer turns image tiles into a sequence of embeddings and uses a learned class token to collect global evidence for classification. It's handy when you want global context and introspectability, but be careful on small datasets. Freeze most weights and train ahead first so you don't destabilize the backbone. A good next move is to unfreeze the last transformer block and tune its learning behavior so the backbone adapts without destabilizing all layers. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.